Hello everybody, welcome back to From Rhythm to Algorithm, part 128, 29, something like that. Math, physics, and linguistics, pointing out empirical evidence, trying to arrive at our axiom. We've proven the existence and the quality of what sensorality is, and today we're going to finish with a very interesting result. We are going to pair sensorality to its unique syllability. And so that's not the final result, but we can kind of approach this problem now from a different kind of angle, right? We said everything is infinitely unique. And so sensorality has to have its own unique definition, and it's relative to other words. And so we've been pointing out its physical intuition, what it means to have feeling, to be sensorial, to physically get sore from tensing your muscles, blah, blah, blah. Go watch the other episodes. But what we have to do is, so we know the solution exists, but remember, language condenses. And so it's kind of interesting to look at language condensing from large-scale history. Where we've used the integration and segregation opposition from the civil rights movement, for example, pointing out the difference, the natural opposite to integration is segregation. Just for a quick example, but point being is, like, physics is condensing logic, or mathematics, the subject matter, like people going to university and studying these things and trying to formalize these proofs in its entirety, right? You have to condense it into that simple aha moment, right? Because it all comes from basic intuition, right? The proofing, the videos, the lecture papers, the conferences, all of that it's not bullshit by any means, but it's not the true moment of insight. And so what you really have to do is, right, get down to that very fundamental base moment of when you have that insight. And linguistically, what it really comes down to is when you condense logic, it has to have a unique syllability, meaning a sequence of letters, representing a unique sound. And so we've demonstrated how we're pointing out the background logic of words and sayings and things we do every day by showing just these different aspects and of the iteration of language and how the words build, contract, expand, and relate to one another. And so our final solution has to have a unique sequence of letters. And so it's kind of a hard thing to imagine, like in the 21st century, right? You have a word with one letter, two letters, three letters, four letters, five letters. And so again, we've done that numerics where it's 3, 5, and it's very clear like the 5 is kind of like the solidifying syllability, words with 5 syllables. But it has to have a finite, unique sequence of letters that hasn't been used before, right? And so that's going to be our final result today, and we're getting very, very close to the reduced form of the proof, but that is what we're going for. And so kind of a longer introduction than I wanted, but it has to have the fact, it's poignant to point out that there is a finite amount of condensed, right? You can only have A, B, C, D, in a certain order so many times, right? Your partitions. How many ways can you arrange combinatorics for linguistics? Nothing more, nothing less. But the fact, right, it's really easy to count. How many ways can you count to 2 with whole numbers? How many ways can you count to 3? But how many ways can you count to infinity, or 1,000 or 100,000, or indeterminately big? And so it's still kind of like intuitively not shocking, but impressive that there's unique syllability left. But we've proven that it's never going to stop. And so, but it just, with 5, 6, 7 syllables, we'll just keep iterating indefinitely forever. But now getting back to the intuition and just different things, tidying up some loose ends of the proof. We were looking for another natural word for base. We use baseball and basement, but again, a natural word would be a basement. And so now towards our final form of solution, we've again talked about how we have complete words, amalgamated words, and complete words, one of those integrated words, amalgamated words, 2 complete words together. Now, for whatever reason, again, the intuition, but the form of the solution is a prefix, a complete word, and then our back to that, the fundamental ing, vibrating, ing is our base syllable. And so, like, for whatever reason, that, like, opens the verb. Like, you take a noun and you put ing at the end, it becomes a verb. And so we're kind of trying to arrange our words into the right order to end with ing. We will get to that as part of our proof today. But abasement, and so you clearly, again, we have a basement. So we're kind of getting to that form of prefix, complete word, suffix. And so we can write that out as a direct logical proof. A basement is not a basement, right? It's literally saying a basement, the room in the bottom of your house, is not a basement. And I forget what the word literally means semantically in English. What is inordinate? Last episode we talked all about and proven a lot of things about ordinality. Inordinate just means excessive, but just pointing out another negative definition with that prefix in front of ordinate. Elementality is used in math with the symbol, a little backwards E will be on your screen. So such that if you write A, that little symbol E, B, like A is an element of B, so you have that phrasing, an element of. And then in the same way you can say A is contained within B with the same symbol without that little line there. But just pointing out again, tightening up the proof a little more. Completeness does not have exceptions, and so this was kind of an interesting thing linguistically pointed out. If you're a native English speaker, if you learn English for indefinite articles, a or an, they will say, you always use an in front of a word that starts with a vowel sound or a vowel. And so the word unique, what sounds more logically consistent or natural to you? An unique system or a unique system, right? And so there's an exception right there, right? You have unique, U is clearly a vowel sound and it's a vowel. And it's much more logically consistent to say a unique system as opposed to an unique system. Direct logical empirical proof right there. Now what do we do with that logic? It's clearly an exception, and completeness by definition can't have an exception. And so what are we resolving there? All operations increase or decrease an element. What about the identity operator? Trying to find holes in my own argument, even though it's impossible and it's kind of a waste of my time because it's proven true that these solutions exist and that this proofing method is legitimate, as if I haven't demonstrated it profoundly at this point. But what about the identity operator? Again, kind of into some intuition where it's like you're always you. It's the only one that can validate who you are as you, but that's more to the physical and biological awareness as opposed to mathematically, like if you just take your identity matrix and times it by a matrix, you just get the same matrix back. And so that's really just the dynamic limit of dimensionality 1, but it doesn't really, the identity matrix, it's a nothing for me, just not important. But the associative and the distributive properties do not apply to division and subtraction. Because, we're getting to what is the correct physical motivation for PEMDAS, for the order of operations. And so we've talked a lot about division and subtraction, why that the physical motivations for those as being first. Linguistically, obviously, subtraction has the most lexical similarity to fraction, right? Subtraction, fraction. Very clearly, division is kind of the first thing you do. Division and multiplication in any of its forms. They are rapid operators, and addition or subtraction are gradual operators. And so, but PEMDAS, we're starting with division, but why not subtraction? I guess, why division as opposed to subtraction? Well, because again, subtraction and division are forms of each other. You're taking something away, you're separating something. And so it's not a meaningful question, I guess. Is it possible to have a fraction physically based with a numerator more than a denominator? And actually, you can see on my last episode, ordinality, I literally stopped, and I'm sure science team knows this behind the scenes, but I literally typed out, it's impossible to have a fraction with a numerator greater than the denominator, which would mean all the solutions, any physical representation of what we use as fractions today would be less than 1, right? If your numerator's smaller than your denominator, it's always less than 1. if your denominator is less than your numerator, your entire set is always greater than 1. And so, obviously, the universe has expanded, things have grown. So, it's obviously, again, the progression case, the increasing operators are more relevant or more something, because then you get, right, they'll say, like, as an English speaker who reads left to right, they'll say addition and subtraction are equivalent. You just do whatever operation comes first as it's written. But then you consider, like, what is the motivation for writing something first? Well, you're starting with your base, whatever, your conceptual base, 3 minus 4, right? You're starting with something 3, and then you're subtracting 4 from 3. So 3 is your base, 4 from 3. And so then we've paired the preposition from, that's to subtraction, this from that to this, 2 is to addition. But then I typed it, I literally can't even remember right now what I ended up putting, but then I switched it. And so it's in orange, it's on the last one, and I was going to explain it. But then again, to our physical motivation, right? If I have this notebook and I divide it, or I subtract something from it, if I take something from it, what happens? Well, again, we have to have our mass consideration. We're not taking, the mass isn't going anywhere. You're just separating the object. So you can't generate more mass that way, but then you have 2 distinct things. And so when you separate something, when you divide it, it then becomes 2 different things. What was the motivation for division? No, the denominator. So the denominator, the mass, because you're starting with a total thing and you're dividing it, the numerator always has to be greater than the denominator. And so you're always going to have something that's greater than 1. So that's why you always have the progressive or the increasing case. That's why there is something as opposed to nothing. But then I just have fractions are always more than 1. It's literally crossed out again in my notebook. So originally I had fractions are always less than 1, meaning the denominator was bigger than the numerator. But from our physical intuition of saying our numerator has to be the base because you have to start with something, I have 1 thing and I divide it by 8 things, and then I get an eighth. And 8 divided 8 times is 1. And so that to me, that is logically consistent. But then I even extended that further and said, do fractions exist? Like at all? And it's on the screen in white in the last episode. And we're saying, of course, I put 3 over 4. Well, again, those are symbols to represent quantities, to represent characteristics of physical systems. And we're physically bounding, we already have physically bounded, but now we're tightening those bounds. And so, well, can you have a fraction? Well, where would we even start with that question? Right? Well, magnetic monopoles don't exist. And so, can you have a fraction of a magnetic monopole? No. It's physically impossible. And so if you divide a magnet any time, you're always going to have 2 poles. So you can't physically or logically have a fraction of a magnetic. Magnetic monopoles don't exist. So we've just reproven that. But with more intuition as to, like, again, why we start with division and why all of our fractions in a physical bound have to be more than 1. It's because the numerator always has to be bigger than the denominator. So that's proven. And that's also true because you can say quark bounding, right? Well, let's get to the most fundamental thing. We can't break apart the electron as a point particle. Absolutely no, it's fractals. I mean, the existence of the word fractals is because fractals exist. And so your shape or your structure of your size scales independently of size. And so that's already proven. That's not even a big step. But then, like quark bounding, you break apart your protons, and you're stabilized 3 quarks in a proton. And so that's all kind of going on there. And so I'm going to stop this episode here and move on to the next one.